Hello, my name is Rachida from the Laboratory of Condensed Matter and Interdisciplinary Sciences at Mohammed V University of Rabat. I'm also affiliated to Materials and Nanomaterials Center at Master Foundation. Today I'm going to present one of our works entitled Improved Magnetic Properties of M-type strontium hexaferrite through nanocomposites. A permanent magnet is a material which is initially magnetized and then creates its own persistent magnetic field, without the need for continuous electric power, and thus no heat generation. Up to now, there are major families of permanent magnet materials, ranging from ferrites, known for their low cost and low efficiency, to rare earth-based magnets which offer a high performance but very expensive. Nowadays, rare earth-based magnets are well known as the strongest type of permanent magnets, although the risk of supply of rare earth elements increased progressively, which required worldwide efforts to develop new materials without rare earth elements or containing little or heavy rare earth elements. On the other hand, ferrites have some interesting properties such as good chemical stability, easy synthesis route with low cost, significant saturation magnetization, and moderate coercivity. These properties make of this kind of materials promising candidates to replace rare earth-based magnets in a wide range of applications that require low magnetic stored energy. So in this work, we aim to improve the magnetic properties of M-type strontium hexaferrite through nanocomposites. To prepare our nanocomposites, we start by preparing the strontium hexaferrite and cobalt spinel ferrite nanoparticles by using the standard co-precipitation methods. Then the prepared nanoparticles were mixed physically using an agate mortar for 1 hour and then calcined at 1000 degrees Celsius for 3 hours to achieve strontium hexaferrite, cobalt spinel ferrite nanocomposites with different molar ratio. For the rest of this presentation, we will refer for the parent strontium hexaferrite and cobalt spinel ferrite as SFO and CFO, while we will use CS5, CS10, and CS20 to refer the nanocomposites with 5%, 10%, and 20% of the soft phase. From the XRD patterns, we can see clear that the CFO crystallizes in the cubic spinel structure, and the SFO crystallizes in the hexagonal structure with space group P63MMC, while the XRD patterns of the nanocomposites show the presence of both cobalt spinel ferrite and strontium hexaferrite phases with no peaks of any secondary phase. The SEM images of the SFO nanoparticles show a hexagonal platelet morphology, while for the nanocomposites we see the presence of bigger and smaller particles, which can be attributed to the presence of cobalt spinel ferrite and strontium hexaferrite nanoparticles. And from the EDX analysis, we can see clear that there is no elements other than cobalt, strontium, iron, and oxygen in our samples. To evaluate the magnetic properties, we plot the magnetic hysteresis loop at room temperature. As we can see from the parent hysteresis loop, the strontium hexaferites have a larger coercivity, while the cobalt spinel ferrites show the higher saturation magnetization. From the hysteresis loop of the nanocomposites, we see clear that there is a good single magnetic phase behavior, which is a good indicator of the exchange coupling mechanism. And to evaluate the performance of the prepared sample for the permanent magnet applications, we plot the maximum energy product as a function of the soft phase content. We can see clear an enhancement of about 26% of the maximum energy products for 5% of the soft phase compared to the pure hexaferrite phase. As a conclusion, the standard co-precipitation rule followed by physical mixing were used to synthesize the nanocomposites. The exchange coupling mechanism have been proved in all nanocomposites, and an enhancement of the maximum energy product was obtained for 26% of about 26% for 5% of the soft phase. Before finishing, I would like to thank all my collaborators in this work from Master Foundation, Mohammed V University of Rabat, GreenMat Laboratory, and the Faculty of Sciences Similaria in Marrakesh. And thank you.